So choosing the right biostatistical test. Okay. I have a friend of mine who works in JSS Medical University. His name is Dr. Praveen, and I have used some of these slides from his presentation. My sincere thanks to Dr. Praveen, who is the Associate Professor of Preventive Medicine, Social and Preventive Medicine in JSS Medical College. Uh, in JSS Medical College, Mysore. So my special thanks for the courtesy that he has allowed me to use some of the slides in this presentation. Always when we do a presentation, it is imperative for any scientific person to acknowledge the help that you have taken, and rightly we are doing that here. Okay, so what we are going to do is choosing the right biostatistical test. Okay. So it is a hard nut to crack. Statistics itself is hard. That is why you came here. If you liked mathematics, you would have been an engineer or a mathematician. Since you don't like much, you have come here, which is a hard nut to crack. But I can make it a banana, of course. It's not that easy, but I can make it very crispy for you. Let us try and make it very crispy, like what you see here. All of your mouths must be watering looking at that crispy stuff there. Okay, let's go down. Think for a while before choosing any test. What is my objective? What am I going to do in this study? Am I going to conclude that there is a difference between two treatments, or am I going to do an etiological study and look at a relative risk and also a sort of odds ratio or attributable risk? Am I planning to prove or test any hypothesis? Is the statistical test really required? Why? Most of the time, you just do a descriptive study. So let us say you have done a descriptive study, fatty liver and diabetes. You will say you have taken fellows under diabetics and found out how many had fatty liver. You come out say 25% of the people had fatty liver. What statistical test does it require? It doesn't require anything. It is a descriptive study. There is no comparison group. And what are we going to do? Don't do any statistical test. If you are doing a descriptive study, just describing the proportion of a parameter in the population, don't do any test. You may say, I have got 25%, out of my 100 people, 45 are men and 55 are women, I will do a statistical test. Not agreed. You should not do. That is not your hypothesis. Your hypothesis is not to test whether diabetes is more common in men or women. In that case, why do you test that? If your hypothesis is to test the fatty liver, then you only have one proportion and 20% or 25%. You can't compare, males and females, the height and weight in the study group and then make a table out of it and put p-values and all sorts of nonsense. Most of the papers do try to compare the baseline information and give you a p-value, which is absolutely not required. You may do it, but that is not your hypothesis. So don't do a statistical test unless there is a need. A simple proportions do not call for a statistical test. Simple case descriptions do not call for a statistical test. Simple case series, 10 cases of myeloid leukemia, I have published. There no statistical test is required. You can't say the age range in these people is this much. I will do a statistical test. Not valid. Unless there is a comparison group, no statistical test is required. Please be understanding that. Am I clear on how my results will look like at the end of the analysis? This is what is called the dummy table. Before you actually complete the study, you can design your 2x2 or 3x3 table like that, and then expect what will be the distribution in the cells. And the dummy table will be filled up once the data is analyzed and the respective numbers are posted. For example, yesterday we looked at 100 people who had undergone 500 people who had road traffic accidents. We had a dummy table first. We started filling the dummy table with our respective data. Okay. Now, what are the types of data you have? Already I have gone through this module for you. Qualitative data and quantitative data. Qualitative data or descriptive data. They are nominal, either names of different cities, male, female, or names of different diseases and whatever is the nominal data. Or ordinal data, like, mild, moderate, severe, grade 1 to grade 5 murmur, or power of this one, or mild COVID, moderate COVID, severe COVID. That is also an ordinal type of qualitative non-numerical data, where it's not the number, but the quality is only described. The other type of data is quantitative data, like height, weight, blood pressure, blood sugar, uric acid, creatinine, estimated GFR, the CT scoring on the given for the COVID. These are all numbers. Okay, quantitative data. Depending on the type, what is the first question you have to ask about the statistical test is my data qualitative or quantitative? The second thing is, are there two groups or more than two groups? Mild, moderate, severe, three groups. Males and females, only two groups. 1 to 5 grade, 5 groups. So like that, you have to decide whether there are two groups or more than two groups. Third important consideration is my data normally distributed? If it is not normally distributed, I cannot use all the tests I am going to tell you now. These tests which are used for normal distribution are called parametric tests. Parametric tests. What is parametric? They have a parameter. What is that parameter? The mean and the standard deviation. The parameter can be easily worked out and it is valid. And that is why they are called parametric tests. How do I know when my population is normally distributed or not? Very simple. Get the mean and the standard deviation. If the standard deviation is less than half of the mean, take it for granted your data is normally distributed, unless the data set is very small, like 3 or 4 subjects. If sizable data set of 50 or above number of subjects, if the standard deviation is less than half of the mean, it is normally distributed. Then what is the purpose of the study? Purpose of the study means, do I want to say that both the treatments are equal and one is preferable because it is cheaper? Or do I want to say these two treatments, one of them is better than the other? Or do I want to confirm etiology? Do I want to test a diagnostic test versus a gold standard? What is the purpose of your study? That also you have to decide. So what are the factors in deciding a statistical test? Is my data qualitative or quantitative? That means only description or a number. Is it a number? Is it discrete or continuous? That's a different story. Are there two groups or more than two groups? Is my data normally distributed or not normally distributed? If not normally distributed, there are ways of converting into a normal distribution and doing the test, or you do a non-parametric test. There are tests called the non-parametric test, which will be done when you have the non-normally distributed data. The purpose of the study also I told you. Okay, is there any difficulty in this slide? Should not be, isn't it? This is all already told to you. Okay, you will be testing the differences between two proportions. Okay, I had COVID disease and I came out with a study where I wanted to analyze whether men are more affected than women. So I have a proportion of men suffering on 25% or 10% or 5% and compare the proportion in women. So there are two proportions. I am testing the difference between the two proportions. Is it really the case? And I would see the proportion of men and women in the community and then see the proportion of men and women in this population of COVID patients and see whether they're any different from the community proportion of men and women. Then you have two proportions. Or you can say, I want to know whether the COVID is mortal disease in people who are more than 65. I classify my patients, those all less than 65 and all more than 65. Make them into two groups. Look at the proportion of COVID in more than 65. Look at the proportion of COVID in less than 65 and compare that against the population less than 65 and more than 65. Then again, you have two proportions. What are we comparing? Two proportion we are comparing in a qualitative data. Second thing is two proportions. There is a control group and study group. You can say there is a study group where I have given vaccine and the control group where I have not given vaccine. The proportion of people who had immunity demonstrated in the study group, there is a proportion in the control group. The proportion of people who had immunity is in the control group and compare them. Okay. Or you can say the proportion of smokers and alcoholics in a case of myocardial infarction. 100 cases of myocardial infarction have taken. What is the proportion of smokers? What is the proportion of alcoholics in myocardial infarction? And compare them with without myocardial infarction and compare the proportion. When you are comparing two proportions, the test that you need is what is called the Z test. Don't ask me how to do the test. That is not the purview of this workshop. If you people who wanted to know how to do the test, we will help you doing that. But there is help on the internet. If you just punch the proportions there and then select the Z test, it will give the answer. So you don't have to really know the back end or back office work, what is going on. In the bank, when you go, there is a front office and a back office. In the front office, the cashier will be there. He will receive the cash, distribute the cash, give you a DD. We do not want to know who is doing all the accounting and keeping track of it. And in the back end, that is a back office work. So likewise, the Z test also, a lot of back office work is there, which we are not interested. Our interest is when to do it and when to apply it and what is the result. Only three things. The how of it is not the purpose of this workshop. Okay. Now, let us see here. So we have done a comparison of dengue knowledge. What we did? We gave a sort of health education about the dengue fever. So the dengue knowledge we are comparing before the health education and after the health education. Okay. Okay, you see, before that, dengue can be fatal. Now, a number of people who said response, 39.7% said yes, they agreed. But after I educated them, it is a fatal disease. They said 78.5. They agreed it is fatal. Then so people, I asked them, it is a virus. Only 26 people knew it was a virus. After my education, 57.7 people understood that it was a virus. Then I also said, is it mosquito borne? Then 63 people knew that it was mosquito borne before, but after my education, 94.9% have said it is this one. So there are proportions here, and what are the proportions here? The proportion before and the proportion after. There are two proportions. Of course, there are three categories, three questions we have answered, and each has got a proportion. This is proportion 1, that is the p-value is there for that. There is a proportion 2, there is a p-value for that, and a proportion 3, p-value for that. So we do a Z test in such a scenario where there are two proportions are being compared. This is not continuous data or a quantitative data. This is just a proportion, whether then yes or no, virus or not virus, mosquito borne or not mosquito borne. That is the response. And such a scenario is the figures in brackets are the percentage, the absolute numbers are on the remaining things. But we are interested to compare the proportion only. We look at the percentage and do a test. Health education appears to be clinically useful because from 39% it has increased to 78% as far as fatality information is concerned. Dengue 26% to 57%. There is an increase in the knowledge about the virus and also about the mosquito from 63 to 94. That means there appears to be a usefulness of the health education. Now the question is, what is the statistical significance of this particular study? There is more than 95% certainty because the p-value is very, very small, 0.001. Anything less than 0.05 is good enough. Then we can conclude in the study, yes, doing health education is improving the knowledge about the disease. Okay. Now, when you have categorical data, that is, categories, nominal or ordinal, but here there are more than two groups. The information on the association, we always say not correlation. Don't say categorical data, correlation. It is a blunder to say correlation for categorical data. This is not a science. So in science, when you say association, in categorical data, only association. In sort of numerical data or discrete variables or sort of quantitative data, we can say correlation. So here association between two qualitative categorical variables, commonest test among all tests of significance is what is called the chi-square test. And again, I am not going to tell you how you do the test. Okay. Now, let us say in COVID and inflammatory markers, we have taken 3 levels of disease, mild, moderate, and severe, and we have done the test, here, the D-dimer test, the interleukin test, and the LDH. So 10% of the mild fellows had D-dimer, and 20% of the moderate fellows and 70% of the severe fellows had D-dimer. Likewise, interleukin also 5% in the mild, 40 in the moderate, 55. These are all proportions. These are not means. So we cannot work out any correlation here. We can only say association of D-dimer with the severity of the disease, association of interleukin 6 with the severity of the disease, association of LDH with the severity of the disease. Because LDH we know is important in the lung injury. So these differences, you see 10, 20, 70, there is a gradation between mild, moderate, and severe. Looking at the data itself. Interleukin 6, 5, 40, 55. That's also showing the gradation. LDH also is showing beautiful clinic. They appear very clinically significant. But then, are they statistically different? Are they statistically significant? For that, I do a chi-square test. If you do a chi-square test, for this, the chi-square is very significant. That means it is less than 0.03 in this particular evidence. This is also a published evidence only I have taken here. Okay, test of proportions, chi-square test. Here, again, another example I am giving, males and females, normal, pre-hypertension, hypertension. Among males, 46, 47, 48 are the different proportions among the total population. Total 4,000 and odd are studied being normal, 1,600 plus are in the pre-hypertension, around 1,200 are in the hypertension. So male-female distribution in the normal were 46-54, in the pre-hypertension 47-53, in the hypertension 48-52. By eyeballing the data, you see 46, 47, 48 doesn't look very different. Likewise, 54, 53, 52, they look almost similar. The differences appear clinically almost the same, that they don't seem to be different. But I do a test of significance of chi-square, and chi-square is more than 0.05, it's around 0.2, and the test of significance is negative. That means it's not a conclusion that there is a male-female difference exists between the hypertension different grades. Okay, one is to show there is a difference, the other is to show that there is no difference. Okay, now that's all about the ordinal data. Now, what about if I have the when I'm comparing the means or discrete data or quantitative data like height, weight, blood pressure, uric acid, GGF or creatinine, cystatin C, any biological variable for that matter, comparing the means instead of proportions, we are comparing the means here. The means can be paired observations or unpaired observations. Paired means, example, hemoglobin concentration before and after oral iron therapy. We assembled 200 women. We gave them, pregnant women, we gave them oral iron therapy. Before that, we took the hemoglobin. After the oral iron, we again took in the same women. Same, that means we have paired observation. Each woman has got one before the hemoglobin, iron treatment, one after the 3 months or 4 months of iron treatment, and you have paired value for each individual. Like that, you have 100 people, 100 paired values. That is called paired observation. Then the hemoglobin concentration is quantified as mean hemoglobin concentration, 10 grams or 8 grams or whatever it is, and there is a standard deviation associated. If the standard deviation is less than half of the mean, then the data is normally distributed. I can do a paired t-test. Whereas unpaired means difference of LDL cholesterol values between men and women. Men are separate, women are separate, but you looked at the mean values of LDL cholesterol. These are called the unpaired observations. Quantitative data, discrete data, where the data are mean and not the proportion. In such a case, is it paired or unpaired? Put that question. If they are paired, then you have to do a pair. If they are unpaired, let us say, data should be quantitative to do a t-test. Quantitative data mean number and not the proportion. There must be mean and standard deviation, and the data must be parametric, that means normally distributed, which means the standard deviation is less than half of the mean. Okay, and there are two independent groups to compare. One group is not dependent on the other, males and females, two independent groups we have. And there is a difference between the two means. And that is what is called unpaired t-test. Okay, unpaired t-test you do. Okay, now you have the next one. So for example, independent t-test cases and controls, uric acid in the cases 3.7 plus minus 1.06. Is it less than 50% of the mean? Yes, it is. Like that, every value you check whether it is less than 50% of the mean value. Mean value 4.7 and the standard deviation is 1.4. So uric acid, cases and controls. And then likewise, SOD is superoxide dismutase. MDA is malonaldehyde. Superoxide dismutase, malonaldehyde, these are oxidative stress markers in the cases and in the controls. And then you see that there is in the controls, the oxidative markers are higher. Compare the cases as you can see here, except MDA, which is the reverse. So you do a paired t-test and the differences appear to be clinically significant. We did an unpaired t-test of independent sample because these are done on cases and controls which are not the same subjects. Cases are separate, controls are separate, and they are not the same group. They are independent groups. So do a independent t-test. Then what happens? Then what is called a paired t-test. Paired t-test is when the data is quantitative, you are comparing the means, data is parametric, normally distributed, mean less than, standard deviation less than half of the mean, variables are dependent on one, pre and post, before, after, this year, next year on the same set of people. And we are testing the difference between the means. So between the pre and the post, and that is what exactly is called the paired t-test we use. For example, here you see the example here. Before treatment, nitric oxide was that much. After treatment, the nitric oxide has come down. What is the treatment I gave? Vitamin E and antioxidant. MDA before treatment 5.5, after treatment 3.99. Vitamin E before treatment 9.95. I gave vitamin E. After 12 weeks, the vitamin E we expect to increase. Yes, it is 13.57. It has increased. Okay. Now, always check whether the standard deviation is less than half of the mean. You can see in this table, every standard deviation is less than half of the mean. That means the data is parametric and it is normally distributed. I can apply a paired t-test. Why t-test? Because these are means. Why paired? Because before, after, same subjects are employed. Okay, that is why it is paired t-test for test of means of a paired sample. So what did we learn till now? Only two proportions, Z square. More than three categories you want to compare, use chi-square. Okay, and then if it is parametric distribution, normal distribution, mean and standard deviation are being compared in independent samples, do independent t-test. Okay, when the same subjects are observed before, after, before intervention, after intervention, before education, after health education, or before they are given anything, and after they are given, before, after you do, or before food, after food, you compare the same subjects, you compare, each individual has got two values, one before and one after, which are paired values, then you do a paired t-test, provided the data is mean and standard deviation is half of the mean or less, to say it is parametric, and then there are two values for each individual, you do a paired t-test. Okay, now, can't be more clearer than this. ANOVA. ANOVA is analysis of variance. The short name for analysis of variance is called ANOVA. This is also for quantitative variable only, but here more than three groups are there. When two groups are there, I can do a t-test, paired or unpaired, depending upon whether it is independent data or paired data. But if there are more than three groups, what do I do? Measured in terms of standard deviation and mean, and then test whether it is parametric or not. If it is parametric, If there are more than two groups, if they are independent of each other, then ANOVA is the answer. So what is ANOVA? You see here, fasting blood sugar, PPBS, HbA1c, and normal, moderate, and severe 3 levels of disease, non-diabetics, moderate diabetics, severe diabetic. Looked at the FPBS, PPBS, and hemoglobin C. You can see by eyeing the data, everything is, the mean is, at least the standard deviation is not more than half in any one of the boxes here. You can easily verify that from the data. First, that has to be verified. And you see 123, 130, 174, 146, 185, 226, 8.1, 8.3, and 10. So which are the ones differing more? Normal and severe are very way away. 123 and 174, 146 and 226, 8.1 and 10. But between normal and moderate, 123, 130, 146, 185, 80 and 8.3, 8.1 and 8.3, they are very nearby. Okay. Now, if you do a test of ANOVA here, why I need ANOVA? It is a parametric distribution because the standard deviation is not more than half of the mean. Number two, it is mean and standard deviation. It is not categorical. It is not categorical ordinal data. It is a discrete data and a quantitative data. And there are more than three groups. For all the three reasons, I do an ANOVA and then do the test of significance. Now, look here, comparison of anthropometric parameters in normal, pre-hypertensive and hypertensive. Height, weight, BMI, hip and waist. Normal people, pre-hypertension, hypertension. So they have taken that and then exactly you do an ANOVA and then there is by ANOVA you get a test called a Fisher's exact test that will tell you between the group differences also. Here also there is no this is a parametric distribution because standard deviation is not more than half. It is in fact very much less than half in all the boxes. Number two, it is discrete data or measurable data in terms of numbers, and then there is a mean and a standard deviation. Number three, there are more than three groups. In fact, 5 groups this way and 3 groups that way. I require analysis of variance. Now, repeated measures. Suppose we do more than 2 groups are there, but on the same person we repeatedly measure, then just like we would have, if there are only 2 groups, we would have done a parity test. But we can't do parity test if more than 2 groups are there. But of course, the distribution is parametric, it is quantitative, but the one is dependent on the other. Each person has got 3 readings, let us say, and then baseline 6 months and 1 year. Then there are more than 3 groups are there. I require what is called the repeated measures ANOVA. It is not the regular ANOVA, you have to do a repeated measure ANOVA. For example, here what I did was parenteral iron therapy has been given at different periods. We are measuring hemoglobin, PCV and ferritin at the baseline at 4 weeks, 8 weeks. See, all the data shows that it is parametric because the mean is the standard deviation nowhere is more than the half and it is always less than the half. Second thing is they are all numbers and then mean and standard deviation. Third thing is there are more than 3 groups. Fourth thing is there are observations on the same individual baseline 4 weeks, 8 weeks. In such a case you do, this is what is called the repeat sample ANOVA. Now, supposing they are non-parametric, that means here you see the mean is 188, standard deviation is 100. It is more than half. 192, 144, 177, 101, 189, 111, 192, 123. All the data is non-parametric. But there are multiple groups here, unpaired observations, government medical college, private medical college, students they have analyzed, textbook reading skills, notes taking skills, memory, text preparation, concentration, time management, they compared. But these are not parametric. When they are not parametric, I cannot use ANOVA. I have to use, these are unpaired. Of course, I cannot use repeat ANOVA. I can't use ANOVA also. Even there are multiple groups. I have to use a test called the Mann-Whitney U test. After the T comes the U. So that way you remember t-test for two observations which are parametric, and it is more than two observations non-parametric, you go for the U. There is another thing called the Wilcoxon signed rank test. The same thing as the previous one, but here they are paired, before and after, pre-test and post-test. You do a health education for rabies, and pre-test what is the knowledge, practice and category, pre-test and post-test, and you have more than two groups which are non-parametric, because 11 is definitely very nearer to half of that, 21, 8.2, 6.1. At least one of the cells it is showing 11.2 versus 6.1. It is not a parametric distribution. So we will probably do a non-parametric test, which is called the Wilcoxon signed rank test. Then when do I do correlation? For quantitative data, the x-axis and y-axis both are quantitative data. Whereas here you see in the previous one, only on one axis it is the quantitative, the other axis knowledge, practice and all their categories. So even in the other example also here, one axis only it is quantitative, the other axis they are very nominal. They are not even categories, they are different names there. But if both the axes are or quantities like weight and height, then I do a correlation. If the data is parametric, we do Pearson's correlation. If it is non-parametric, we do Spearman's correlation. So for example, you see height, 100 centimeters to 200 centimeters. In the x-axis, weight from 20 kilograms to 120 kilograms. It is put there, and you see a beautiful, perfect, near perfect correlation. This correlation coefficient is the statistic that is worked out. It is almost nearing 1. 1 means perfect correlation. Anything nearing 1.9, 0.8 is a very good correlation. So for example, here, look here, it can be negative correlation also. Age versus EGFR. Glomerular filtration rate comes down with age. 10 years to 90 years, what was 120 or 110 at 10 years has come down to around 50 or 60 by the age of 80 years. So this is a negative correlation where R value is the correlation coefficient is designated by R, and it is minus correlation because with the age, the correlation is coming down. That is the negative correlation. Understand, correlation is done when this variable on the x-axis and on the y-axis, both the x-axis variable and the y-axis, this is the y-axis variable and this is the x-axis variable. Both the variables are numbers. Both the variables are not ordinal or nominal data. Okay, regression. When do I do regression? Regression is to predict the outcome variable using a set of exposure variables. The best example I can give you is yesterday, you would have seen in the cricket, 20 overs, if the score is, let us say 60, they will project and say what will be the score at 40 overs or 50 overs or 20 overs in a one-day match. In a T20 match, what is the score at 8 overs? They will predict at 15 overs and 20 overs. This they use what is called a logistic regression. They use a regression to arrive at that. Why do we need in medicine this one? Supposing I know the mortality trend at 40 years, I can say what will be the mortality at 60 years or 70 years or 80 years. Or cure rates. If I have observed for 1 year what is the cure rate, I can regress and say what will be the survivors or cure at the end of 5 years. So this is what is called, you predict something in future using a regression test. Whereas in correlation, you don't have any prediction. The best example is we are predicting the predicted score, they will say. If the average score per over is 6, this is the prediction. Average score is 8, this is the prediction. Average score is 10, this is the prediction. So several calculations will go in how many batsmen are out, what is the average strike rate of the batsman to come in, what is the strike rate of the bowlers to bowl more overs. All those things they factor into that and produce a regression and give you an estimate there. This gives an estimate of what is going to happen about the outcome in future time. This is important for us to know, something like a Jatakam, which tells you in future what happens. Now here, in the regression, there are several regressions: simple linear regression, multiple linear regression, logistic regression, polynomial, multinomial regression, Cox proportional hazards regression. So many are there which are out of the scope of you. This is only to tell you there are the various ways of regressing the data and then projecting in future time what will happen. So with this, I'm going to end the presentation on this one, what is called the statistical test, and let us take the questions there in the worksheet.